So popcorn kernels, right? So imagine this little kernel, okay? Inside that kernel, besides the starch, that's what popcorn is water, okay? You put it in the microwave, like Bryce said, or on top of a fire if you're, being rustic, okay? And the water inside the kernel starts to move, okay? Literally, popcorn kernels are like tiny, tiny bombs. Because all a bomb is a closed-in explosion, okay? It gets to the point where it can't withstand the pressure, and so it pops open, and the starch flours out, the steam comes off. This is why every bag of popcorn, or every time you do popcorn, you have kernels that no matter how long you heat it, will actually never pop. It's because they don't have enough water inside of them to build up the pressure. It's the same reason why popcorn can expire over time, is because they dry out too much and it will never pop. Okay? So this idea of having water trapped inside everyone is actually the same idea of what a hydrate is in chemistry. A hydrate is a molecule with water trapped inside of it. I have an example, and I'll bring it around so you can see, but I have an example of what is called copper chloride. It's actually called copper 2 chloride dihydrate. Hydrate molecules are molecules that have water trapped inside of them. So copper 2 chloride can exist without the dihydrate. But this particular example has it trapped inside. Okay? Where's my clean beaker? Let's write this first. So the formula of hydrates looks something like this. Is you have just the regular chemical formula. Once again, we'll learn how that works down the road. For the hydrate side, you put a little dot, kind of like a times symbol in math, and then how many waters you have. Di is for 2. Trihydrate would be 3, so on and so forth, different prefixes accordingly. Okay? Sorry, let me get a clean beaker so I can pour this out so you can see it. So what's crazy about it is molecules and water molecules are so small, you can't really see it as it is right now. This is a really pretty looking chemical here, nice color to it. But if you look at it, does it look wet? Oh no, don't go there. Okay? But yeah, you can't really see the water. It's not like it's dripping away, because it's literally trapped inside the crystal. Now, if we can get the crystals to open, you can actually get the water to come apart. So this is not a chemical bond between the two. That's why when we write it, right, they're written separately, going back to the differences between a pure substance and a mixture, right? Now, it's a little bit more than a mixture in the sense because it's kind of trapped within. But if I put this on my hot plate and heat it up, it won't explode. The water will actually just evaporate away. It takes quite a while, but here's what I get. So this is literally the same thing, but we've now lost water, which is interesting because it also loses its pretty green color, right, when the water goes away. Yeah, Kimberly.
So how did we find out what substances had water trapped inside? How did we discover that?
Oh, how?
Yeah. How do we determine?
So often in chemistry, I don't know if there's so much found. I'm not positive, but I'm guessing a lot of them we make that way because it helps in certain chemical reactions to have it be hydrated versus not hydrated, because having the water there just helps the reaction. I don't know in terms of when they first found it, if it was found or made first. I'm not sure. I'll look and let you know. Good question. Yeah. Any other questions of what a hydrate is before we get into some math with them? Yeah, Carly.
So you said it like helps in reactions. Like, what does it do in reactions?
So because water is a liquid, and we'll get once again more into this kind of as we go, things don't typically react in solid form, right? Two solids don't typically react because they don't have enough energy and movement. So the water provides more movement of the molecules as it gets released, and so then it can react better. Does that kind of make sense? So, good question. Okay, take a look at exercise 1.3e, and let's kind of break down this data. So they're telling us that we have a certain hydrate molecule here, known as sodium sulfate, but we don't know how many hydrates it has attached to it. So our goal here is to find in a sense, the ratio of compound to water. So this should have a similar type feel to what we just did with empirical formulas, because empirical formulas were just about ratios, right? The difference is we're looking a little bit bigger of substance to substance instead of atom to atom. Okay? All right, let's read our question, and as I read, let's underline all the given information that will probably be valuable. Okay? So when a 3.22 gram sample, so underline that number, of an unknown hydrate is heated, the water is driven off. The mass of the anhydrous substance, anhydrous means the water is now gone, okay, that remains is 1.42. So underline 1.42. The value of X in the hydrate is what? So our goal is to find this. We're given two pieces of information, but raise a hand, anyone have an idea of a good first step would be here? Yeah, Evan.
Change it to moles.
Ooh, we will need moles eventually. Always a great idea. But there's something we want to do first. So hold that step for later. Taylor?
Subtracts the 1.42 grams from the 3.22.
Yeah, we need to find how much water we have or how much water left. So this was with water. Because that was beforehand, right? The before. We had, what was it, 1.42?
Mm-hmm.
That's after we heated it, so without water. So if I subtract those from one another, you get 1.80 grams of water was in my sample. Now, Evan, why did you say we need to change it to moles? Because that's what we want to do next.
Because we're trying to convert it over to, like, the same thing that we did last time.
Good, yeah, and the ratios are always based on moles, right? Never grams. The thing you gotta learn in chemistry is we work in grams, but chemicals work by moles. So there's always kind of that connecting piece, okay? So now I'm gonna take my grams of water, 1.80 grams, and convert that into how many moles of water were in my sample. So grams of water to moles of water. For every 1 mole of water, it has a molar mass. The problem tells me 18, by the way. If a problem gives you a rounded number, you can use the rounded number.
I like round numbers.
Okay? So we get 0.1 moles of H2O. Questions so far? Okay. Ideas on a next step. I now know how many moles of water I have. Kind of try to compare it to what we did last time. What else do we need? Yeah, Evan.
Should we find how many moles of sodium sulfate we have?
Perfect. Because it's a ratio, right? So we have no moles of this, we need to know the moles of the other thing. Okay? So this was without water, so that's how much sodium sulfate we have. Okay, so I'm going to take my 1.42 of my sodium sulfate and convert that into moles. Once again, it gives you the grams of 142. If it didn't give you that, once again, that's just the molar mass added up. Okay, so this one ends up being 0.01. So now we found how many moles of our substance. We found out how many moles of water we have. Isaac, you have an idea?
We divide both by 0.01.
Good. So now, just like last time, we divide by the smallest to find the ratio. You may also be able to tell what the ratio is because of these numbers, but so we divide by the smallest, we get a 10-to-1 ratio. So this substance is known as a decahydrate because it has 10 water molecules trapped within one of the other ones. Yeah, Kimberly.
Is that like abnormally large or is that normal?
Like there's other ones that are decahydrates as well.
Okay.
Yeah.
Do they show up often?
Say that again.
Do they show up often?
I don't know. I've never really tracked all the hydrates, but I know I've seen others that are. So it's not like extremely rare. It's probably one of the biggest I've seen. I don't know if I've seen much bigger than Deca.
Okay.
You have to have a pretty big crystal to fit more than 10 inside of it, right? I'm not sure. That'd be interesting to know what's the biggest hydrate molecule. I'll look and see. I'm curious. Any other questions? Yeah.
How do we write out our answer to?
So in this case, your answer would actually be just putting it into the formula. Yeah. Yeah, so you just write that your final answer is, and then 10 H2Os. Okay. Put your notes like aside. We're going to come back to them in a second and pull out just a lined piece of paper. Okay, if you think about it, okay, one other thing that you could distinguish with pure versus a mixture. We've been talking a lot about this idea of ratios, right, or proportions. A pure substance has a set ratio. For example, water is always 2 hydrogens, 1 oxygen, right? It's always 2 to 1. A mixture, that ratio can change. Meaning if I have oxygen and hydrogen together, right, I could have 4 to 1, I could have 3 to 2, right, because that's just however much you literally pour in to your flask or whatever you're measuring in. But just kind of another way you can think about it is that ratio idea or proportions. Okay? Okay, let's talk about our gravel and water. So coming here first, this group, thoughts on separating our gravel and water mixture?
Strain it.
Strain it, okay. Oh, let's give them a hand. Okay, this group, different idea, same idea?
Yeah, use a filter or strain.
Filter, strain, okay. Same, anything different?
We had strain it.
Strain it, okay. Very good, and that is the best way to separate, in chemistry, a solid from a liquid. Okay, in chemistry we call it filtration. These are in your notes, they're just not in the order I'm talking about them, but you should see like headings for each. The really scientific name for filtration is known as gravimetric analysis. I know.
Wait, isn't that like the gravity?
But it's literally because it's just using gravity to separate them, right? But it makes it sound really high tech. Okay, so don't be frightened if you read a question that says that they separated through gravimetric analysis. They just filtered it. Now in chemistry we don't use strainers in such a way like you do with like spaghetti, right? Because we need something with very, very, very small holes so the molecules can separate. So we just use filter paper, which literally is the same thing as a coffee filter, and we'll actually use these in lab because they're cheap, but they work great. Okay, so this is a filter paper. Pretty much how it works, right, is if I were to take this, pour it on here with obviously a cup underneath, the water would catch, the rocks would stay, and I have my separation. Okay, so filtration is the best method to separate an undissolved solid from a liquid. Now this undissolved solid actually has a few technical names that we'll talk about. Is number one, when something doesn't dissolve, we say that it's insoluble. Okay, so insoluble means not dissolved. Yeah?
So if something's taking a little bit to dissolve, would it be considered insoluble and then soluble once it's fully dissolved?
So normally you don't give the label of soluble or insoluble until after you've given it time to stir and sit. Yeah, good question. Because technically you pour salt in,
Yeah.
it may not dissolve right away, but it will eventually.
Or,
Yeah.
This is a little scary. So if you put like a body in water, it's technically soluble, right? But it will take a while. And so would you say it's insoluble? I know it's weird. I can't think of another option.
Yeah, I don't know. Is the human body soluble?
Right, because the water will break it down.
I think the difference though is this is my thought on it. I have no idea officially. Really hypothetical, right? I would say that you'd say it's not soluble because it's really more of like almost a reaction with the water that's making it like,
Okay,
do you know what I mean?
right, not like,
It's not so much that it's just like, because your skin doesn't dissolve in water.
right, you can swim and be fine.
Yeah.
Yes.
But it's because the body's breaking down,
Right, weird.
and it's almost like, it's kind of like the idea of like rusting, right? When something rusts, you're not really saying that it's soluble because it's reacting with the water.
Yeah.
But like when something rusts, it does get smaller, right? So that would be my thought on that one. But I'm not positive. Another word as well is we call this thing a precipitant. A precipitant is an undissolved solid in a liquid. Now, one big thing with the filtration process is you have to make sure to dry completely. Meaning, once again, I don't know where I just put my paper. Oh, here, but nope, that's not it. That's different. Oh, it's right here. Okay, if I poured this on, let's say I wanted to measure how much precipitant I got, right? If I pour that on and I capture the rocks, and then I just initially go and put this on a scale, that technically is going to be heavier than what you really have because there's still water present. So after you filter something, what you do is you have to give it time to dry. Now you have two options. One, you just let it sit in the air and it will take a few days. Or we have drying ovens where you just put it in the oven and let it dry. Put it in the oven, let it dry. How do I know when I'm done drying?
If it's not wet.
True, but you got to think at a molecular level, every little water molecule can be hard to see. How can I guarantee that all my water is gone?
If you can light the paper on fire,
The wet things can still burn.
that's true, but it's harder. So you
I like
compare-
the ideas.
You compare it to a normal copy paper and the other one, and you see if it takes extra long to burn.
Kind of. Except we're not going to burn it, but we are going to do it in a sense of comparison. We just take it by mass, right? So you take your wet one, you weigh it, you then dry, you weigh again, you dry, you weigh again. What am I waiting for?
Oh, till it's exactly the same.
So it stops changing, right? Once it stops changing, I know all the water has left. So, or we burn the paper, the other option.
Set it on.
Fire seems to always want to be the answer, Taylor. Right?
Well, you know what? If it works, it works, right?
Questions on filtration? Okay, very good. Okay. Second solution, salt water. We'll start with this group this time. What was our idea here?
Boil and contain the water vapor. So like you boil it and then you keep like the vapor so it can become
So the
water.
salt stays and we catch the vapor.
Yeah.
Great idea. Same, different idea? That group? Same idea? Most people come up with the same one on this one, and that is the best way to do it. It's known as the evaporation process, right? Hence, we're forcing it to evaporate, leaving behind the dissolved solid. So evaporation is the best technique to use when you have a dissolved solid in a liquid. A dissolved solid is known as soluble. So insoluble is undissolved. A dissolved solid is known as soluble. Pretty simple, straightforward technique, but useful at times. Questions on that? Okay. Oil, and water. We'll come to this group. What are our ideas?
So we looked at we looked at the freezing temperature of oil and water, and the freezing temperature of oil is 37 degrees, while water is 32 degrees. And so we decided to freeze the oil at 37 degrees, and then take out the frozen oil, and the water will be frozen yet.
I like it. Very good idea. Back row, what was your idea?
It was actually the same thing.
No.
Really, you guys also thought freezing point as well?
Yeah.
Did you guys have a different idea?
I thought
We
that
just said
was
let the density separate it out, but that might not work because it'll be harder to pour it out. So that was two different mechanics.
Okay, so you're just saying just like pour.
Yeah.
Actually, we'll talk about a way that you can do that that actually would work really well. So density actually is a great option. This group, different idea from someone else?
We had a couple answers.
Yeah.
So we did the freezing one at 37 degrees, we thought. And then also you could put a liquid with the same density or with a like medium density
Okay.
in it, so it would like there'd be something in between, then you could separate it. And then yeah.
Okay. No, not a bad idea. The freezing one, I applaud for thinking. I didn't even think of that as an option. I assume it would work. I'm gonna go and try it because I really want to know.
My only hang up with it is that the oil is on top of the water, and so if we freeze the oil, then how are we gonna get the water out besides like breaking the beaker?
It would just
If
Do
you
think
have
it
a,
would just slide?
if you had a really cool design feature,
Yeah, you have to you have to have something. I'm just gonna
Open it from both ends, maybe like a beaker that was like a cylinder.
I'm gonna do it like in an ice cube tray at home and then like see if I can just dump out and see if the
Yeah.
water's still liquid. I don't know, but yeah, great ideas. In chemistry, we don't often use a freezing method for things, but once again, you're getting to the point that the whole idea of separating mixtures is you got to think about differences of properties, right? Now, another way actually is really with just gravimetric analysis again. Rather than pouring it out per se, if I just poured this into a flask with like a funnel at the bottom, I could just let all the water drain through and then stop it before the oil comes through. Right, so it's actually just another twist on a gravimetric analysis. Food for thought, I don't need you to know the answer, but with this idea of density, right, because a lot of you kind of thinking about it in that way. Density is not the only reason why these two things are separate.
Oh, that's
Just something kind of keep in mind, because alcohol and water have different densities. So just kind of, once again, we'll kind of answer that as we go, but just kind of food for thought. We're thinking chemically minded, right? Be careful with the thought of density in things. So, okay, very good. Okay, let's go to the next one. We just came to you guys. Okay, back row. Alcohol, water. How are we going to separate this guy?
So we thought that we could do kind of a distillation kind of thing where since alcohol has a lower boiling point than the water, then we can boil the alcohol out and then we have two separate things, capsicum.
Yeah, great idea. Front group, did you guys have an idea?
Ours is just always a mixture.
Boiling as well?
Yeah.
Different idea? Boiling as well?
Yeah.
Okay. Yeah. Hold that idea, because we'll kind of talk about it. Problem is, alcohol is also polar.
I thought so, and that's why they're mixing, because otherwise.
But
Yeah.
you're onto something actually that's going to be really important in a second. So, great. Great thought for the boiling, because that is actually the best way to do it. And like Max said, the official name for that type of separation is known as a distillation.
There we go, Max. How did you know?
Are you guys okay if I erase these? Everyone got that down? So we can see our picture?
I have a question.
Yeah.
What's the difference between distillation and evaporation?
So evaporation is to separate. It's actually, that's a good question, because they kind of have a similar idea because we're boiling, right? So distillation is used to separate a liquid-liquid mixture.
Oh, okay.
They have to have different enough boiling points. Because technically with the salt water, right, I technically wouldn't even have to heat that. I wouldn't have to boil it. That would be a fast way to do it. But if I just let this sit for days and days and days and let it evaporate, I would get the salt left, right? The difference is with distillation, if I let the alcohol and water just sit for days and days and days, it's not going to separate out on its own. Does that make sense, the difference? Great question. So here is a chemistry setup for a distillation. Now, this is literally how people make moonshine, side note. Not encouraging that at all. But that literally is the idea, is you're trying to make a very pure sample of alcohol and get rid of the water. Okay? So here's how it works. Okay? So here's our alcohol and water mixture. Okay? Alcohol boils before water does. I can't remember the numbers. What's the boiling point of the alcohol? Someone look it up.
172 degrees.
Okay, in Fahrenheit it's 172. Okay, and water doesn't boil till 212. So it's a very, very controlled process. You can't just crank the heat, right? Otherwise they'll both just boil away. So what you do is you heat this very carefully to 174 degrees. At that point, the oil in here, not the oil, the alcohol in here will start to boil, turn to a gas. Inside this chamber, now I don't have this equipment, that's why I'm showing you a picture. This is something I'm hoping to get this year with some of my fees that I got, or funds that I got from last year. As it travels up the chamber, there are tiny little pieces of glass stacked like stairs. The point of this is what happens is the gas goes up, and then the glass up top is a little cooler, so it will condense into a droplet and land on a step. Eventually it will heat up and climb up to another step. Heat up, climb up to another step. So literally the little droplets are like climbing up the ladder until eventually it gets to here, and then as it travels to this point, this is a tube inside of a tube. Okay? The outside tube gets hooked up and gets surrounded with water. So then when it comes here, it turns back into a droplet because of the cold water, and then drips out, and here's your pure alcohol. The whole point of this little staircase thing is, once again, just to really purify the sample, right? Just to really guarantee that only the alcohol is coming out the other side and the water is staying behind. But it can be quite a lengthy process. I remember doing a distillation in college that took about 4 hours of just watching literally something boil, right? But you can't go too fast because otherwise it wouldn't be pure in the end, right? Which is the whole point of distillation. So, questions on the distillation process, how that works? Okay, oh yeah.
Is it typically like 100% pure at the end?
Depending on how good a job you do, it can be. 100% obviously is really hard, and obviously depending upon equipment, right? Obviously in like high-tech labs, they have like equipment that manages it, which would control it a lot. Like in college one time when we did it, we'd actually often would then take this sample and redistill it again to like make sure it's pure. So yeah, because 100% obviously can be difficult. But obviously if you were like a commercial business, then you have other means to make it better. So yeah, great question.
How do you like assess how pure it is?
Through some different types of equipment, you can then like, we won't, do we ever learn it in here? Oh, I think we will. So we'll learn about some other type of spectroscopy. So we talked about mass spectroscopy, but there's also infrared spectroscopy and UV light spectroscopy, which can help identify purity of substances. Yeah, so there's like cool equipment that you can put it in and it'll tell you how pure it is, or if there's other things present. So yeah, good question. Any other questions on distillation? Okay. Let me make sure there wasn't something else I wanted you to write. Obviously, once again, key thing, they have to have different enough boiling points. If their boiling points are too similar, it gets too hard to separate them out, right? Because they just both get traveled up the process. So, okay, let's hear some creative ideas. This is always the hardest one for people. Anyone want to share thoughts on how we can separate our red and blue food coloring?
You drink it, and then your cells will absorb the water, but they will not absorb the red and blue food coloring.
Oh.
Did you want the red and blue?
Well, they'll absorb the red and blue food coloring separately.
They'll absorb them separately. That's funny. Someone last period wanted to do that with the alcohol. They said, we'll just drink it and let the liver separate it. True, I guess. But. Any ideas? And I don't blame you. This one is...
No, we have a good one.
What's your idea?
We were
Chromatography.
super confused, and so we just decided that we'd invent a color magnet, and yeah.
Ooh, so they're going to invent a color magnet. Okay, so this one only attracts red,
Correct.
and this one only attracts blue.
Yep.
It's
Baby, that's how it's done.
Anyone else have an idea?
chromatography.
And I gave it away because it's in my paper. But chromatography kind of works through the idea of magnets. Kind of. In a molecular size kind of way. So chromatography is our last type of separation technique. By the way, chroma means color. So that's where it gets its name from. Chromatography is used to separate liquid-liquid mixtures that have different colors, typically. There is actually a type of chromatography where you can do it under like UV light. So to our eyes it may not look like it has different colors, but then you shine a black light on it and you can see the separation that way. We will do a lab later on in the year of chromatography. So you don't need to understand all the details of it per se right now, because it will make more sense when we actually do the lab, but here's kind of the basics of how it works. And it really is this idea of kind of magnetic forces. Now, it's not a magnet in the sense of like metals, but there's a lot of forces that happen at that molecular level. And those forces play such a big role in what things do and what they don't. So, where did my theme go? Okay, so, for example, black ink is actually a mixture of a lot of different colors. You may have done this little activity like in elementary school or something where you take black ink, draw a dot, and then you put some water on it. Or sometimes they do this with like t-shirts and alcohol, and you make like a tie-dye t-shirt that way, if anyone's done that way. But this was a black dot that I then dropped water on, okay? It's not, I should have maybe done a little bit longer, but can you kind of see some of the different colors in there? The blue's very obvious, right? And then you can kind of see there's a little bit of yellow right there in the middle, and then kind of some red. Once again, it's not the perfect separation, but it kind of will get us thinking. So the idea of chromatography is this, is that certain substances are attracted more to other things than the other substance might be. For example, in this case, because the blue color spread the farthest, the blue color is more attracted to the water than it is to the paper. The yellow color stayed almost exactly where I put it, which means it's very attracted to the paper because it's latched onto it. So that's kind of the idea with the magnets, is it's what it's more attracted to. So chromatography works through figuring out, okay, what's going to be attracted to a paper surface versus what will attract to a liquid surface. And now it can be water, you can use lots of different substances, and then we have very specific types of chromatography paper, where the paper, once again, depending on what substance you're using, is determined by which paper you want to pick. That's kind of the basic idea of how it works for now. So, general questions on that? Okay. Any other questions on lab separation techniques? Okay, turn your notes to the next page for me. Let's just take a look at an example of an AP question. Okay, we're not going to go through this whole question, but I kind of want to use it just to start teaching some things, some different points to understand. Okay, I'm going to go do part A for you because we haven't learned how to write formulas yet. We will eventually, but not yet. So just write this down under part A. So the reaction that's happening here is we have some potassium iodide reacting with lead nitrate. And it's making potassium nitrate and lead iodide. Now, something I want you to start getting familiar with, because you'll see it, and maybe you've already seen it in your textbook, is with the chemical equation, we'll write what's happening in terms of it was this and now it's that. But then we'll also label each substance with a small little subscript. Okay, so write these in. So right next to this one, write a little AQ in parentheses. AQ in chemistry means aqueous. That it's an aqueous substance. Any guesses of what aqueous means, or someone remember from last year? Something with water, right? So aqueous means it's dissolved in water. Okay? In this problem, this one is also aqueous. This one is also aqueous. That one is a solid, so we write an S. Which means it's not dissolved, which also means then this is our precipitant. Two other symbols you might see in problems, and you could see a little L. Typically the L is written in cursive, so you don't confuse it as the number 1. Okay, so if you see an L, what do you think that means? That's a liquid. And then G means it's a gas. So it's important to understand in chemistry the difference between these things. If I write NaCl like that, what does that mean? So that's solid table salt, right? Like sprinkling it in. If I write it like this, what does that mean? That means I melted my salt and turned it to a liquid, right? Versus this, what does that mean? So that means I'm using salt water in my experiment, right? This would be extremely rare, because to melt salt, it has to be like at 1,400 degrees or something like that. In Fahrenheit. Celsius, I think. I just have that number in my head. But I'm pretty sure it's Celsius, because most times I keep track of Celsius. Yeah, so crazy, crazy hot, right? So normally that wouldn't be the case. But, okay, now, look at problem B, and I just want to end on this before the bell rings, okay? Read question B and give me a short answer based off what we've talked about so far. Just as kind of a recap here. Okay, turn to your table, buddy, and tell them what you wrote. So, what I want you to recognize here, I think I heard the right thing from everyone. So the whole point of drying 3 times was to make sure all the water is removed. So in solving this problem with that data table, this last one is really the only number you care about, okay? You've got to learn how to sort out, like, I need to use this information, and this is just like they're telling me information. It's important that it's there. I wouldn't say they don't ever give you something that's not important, but there might be data and numbers that you never use, but you can get caught up in thinking you have to use them somewhere. So really the best thing to do is when you read a problem is create a picture of what's happening, right? So that it can make sense of what's going on. The other thing that I want to make sure we start practicing, and that's why I have you write it out, is getting really good at writing clear, concise answers. We don't want to be wordy because we don't have time for that. But we also want to be very clear what we're doing, okay? Homework is pretty short tonight, so if you're behind, get caught up. You just have a reading